Okay, team, let's look at an example of a binomial distribution problem. So I'll set it up. We are looking at the annual rainfall for Orange County, California. And we're saying that it follows a Gaussian or normal distribution. So Gaussian is just another name for normal, named after Gauss, who, I don't know, discovered the normal distribution. And we are saying the rainfall in a year follows a normal distribution. So it has a mean of 15 inches and a standard deviation of 4 inches. So we'll say X is the annual rainfall in inches in a given year, and it follows this normal distribution. So the water supplier for Orange County declares a water shortage if by May, only 7 inches of rainfall has occurred or rain has fallen in the preceding 12 months. All right, so we look back, we say, have we had 7 inches? No, okay, we've got a water shortage, so we need to cut back on watering all those lawns. So here's the question. What is the probability that we'll have at least one water shortage in the next 5 years? So this is ultimately our binomial question. This is where we get our probability. So let's talk about how to solve this. First, we need to calculate P. P is our probability of success, in this case, the probability of a shortage in a given year. So that's how we're defining success. And ultimately, because the probability of this shortage follows a normal distribution, we have to go to that normal distribution. So in this case, we're looking at the probability that X is less than or equal to 7 inches. Okay, so this is our P for our binomial distribution. And then second, we need to use the binomial distribution to calculate the probability of one shortage over n is equal to 5 years. So if you look at our binomial distribution, it's the y and n are the two parameters that we put in. So y is the number of successes over n trials. In this case, we're saying one success or one shortage in over n years. All right, so let's solve this problem. First, we're going to do this first part, right? So the probability of our shortage. So we said that X follows our normal distribution. All right, so the probability that, let's make this a little bit narrower, that X is less than or equal to 7 is really just equal to phi. Remember, phi is where we use the cumulative distribution function, X minus mu over sigma. In this case, X is 7. We're looking for less than or equal to 7, so we can just plug that in directly because we want that cumulative probability up to 7. So we'll do 7, the mean was 15, and the standard deviation was 4. And so this ends up being phi of -2. And if we go to our table, or we could do P norm, where we put in -2 in R, or we could do P norm 7, where the mean is equal to 15 and standard deviation is equal to 4. And that will give us an answer of the probability of shortage is equal to 0.0228. We'll keep that level of precision just so we can propagate that through. All right, so now we're going to use the binomial distribution to calculate the probability of one shortage, y, one success over a trial of 5 trials or n years. So y is equal to the number of successes, in this case, shortages. Now remember, success always doesn't mean you're winning, right? We looked at that example of sickle cell disease, and they defined the success as the probability of having the disease. And then n is equal to the number of trials. In this case, it's years. So each year is a trial. So we want to look at the probability that we have at least one shortage. So that's kind of a key thing here. So at least one shortage. And really what we're calculating here is the probability that y is greater than or equal to 1, right? So it could be 1 shortage, 2 shortages, 3 shortages, 4, 5. So the way this works is we're going to flip it so that's a little bit easier. So the probability that y is greater than or equal to 1 is equal to 1 minus the probability that y is less than 1, right? Which is equal to 1 minus the probability that y is equal to 0, right? So less than 1 just means 0. We can't get less than 0. So this is ultimately what we're going to calculate, just to simplify it, right? If we wanted to do greater than or equal to 1, we would have to add up all the individual probabilities for y is equal to 1, 2, 3, 4, and 5. But this makes it a lot easier. So we'll go to our binomial distribution. So the probability that y is greater than or equal to 1 is equal to 1 minus the PDF, which is n choose y times p to the y, 1 minus p to the n minus y. So n is equal to 5. And in this case, we're going to say y is equal to 0 because this is what we want to calculate, right? So we do 1 minus 5 choose 0 times our probability 0.0228. Y is equal to 0, so we put that in there. 1 minus 0.0228. And let's get this stuff out of the way. Um, 5 minus 0. And then we can calculate this out, and we end up with 0.11 or an 11% chance. Now, how do we do this in R? So we talked about how to calculate the normal distribution in R. Well, in R, the binomial distribution is, actually, let me just erase that. It's a little rich for my blood. We use functions such as D, so D is density, bin for binomial. We can use P, which is the, P bin. And we can also use Q bin, and then R bin. So R would be a random number generator for the binomial distribution. So these are the functions we can use. And the way we would calculate this, so this is the PDF right here. So D bin is density. So this gives us our probability density function, or in this case, it's really just a mass, right? Probability mass function. This is our CDF. And then this is the inverse CDF. So this is like your phi function, right? If this were the normal distribution. Sorry, that's not correct. The way this works is if you plug in a probability, it gives you the number of successes over n trials. Okay, so let's do this calculation in R. And we had 1 minus the probability that y is equal to 0, right? That's the probability that y was greater than or equal to 1. In R, we would say that this is just 1 minus d bin, because this is our PMF. And then we put in whatever x, or sorry, we could just say y value, whatever y value in here, n, and then p. So this is our probability that we already calculated. This is the number of trials, and this is what y is equal to the number of successes. So this would be 1 minus d bin, 0, 5, and then 0.0228. And that's going to give us the same answer that we got, so 0.11. So here, the binomial distribution, we just plug in y, so the number of successes we want to calculate, the number of trials, and then the underlying probability of an individual success for an individual trial.